Hi, everyone. Today we're going to talk about LPs and CDs. This is an example to first start with radial and tangential acceleration, then how linear and angular velocity relate to each other, and how changing one changes the other and whatnot. And we'll use LPs and CDs as an example. So first we have 10.9. It says it's about radial and tangential acceleration. So this is something that we've talked about before. We actually had the equation, right, that the square root of tangential acceleration squared plus radial acceleration squared, that gives you the overall acceleration of a rotating body, right, or of circular motion is what we called it back then. So recall that there are two kinds of acceleration. So there is tangential acceleration and radial acceleration. So if I draw, that's not bad. So we've got tangential acceleration, right? Buds off along the tangent. And then you've got radial acceleration that goes right along the radius. Okay? If you combine these two accelerations, then you get that A, just like we were talking. Now, when we talk about tangential and radial acceleration, these both change velocity, but velocity has two components to it, right? Velocity is speed plus time, plus direction, not plus time, plus direction, right? Speed with direction is velocity. So we know that radial acceleration is all about changing your direction, right? That's what causes you to go in a circular path like we talked about last semester. So radial acceleration causes change in direction. And then that means tangential acceleration is going to cause change in speed, which is true, right? If you want to change the speed of a rotating object or of circular motion in general, you need tangential acceleration. If you want to make a tighter turn, then you need to increase your radial acceleration, right? So that's how radial and tangential acceleration have this relationship together. Now, the next question asks, is the alpha in alpha equals delta omega over t tangential or radial? So that's a good question. Let's look at, oh, that's a bad circle. Let me see if I can actually get a circle. It's not bad. Okay, so we'll start with that. So we've got radius r, right? If we want to know if that acceleration is tangential or not, let's look at 2 points. Okay, actually, you know what? Let's just look at 1 point. We're going to look at 1 point P, and it's going to make a rotation over to this line right here to another point there. Okay? Now, if we want to look at its change in position, okay, the change in angular position, we know that that is, it's not moving any closer or further away from the radius, right? So that would be tangential. Its change in position is perpendicular to the radius, right? It doesn't get any closer or further away. It's perpendicular to the radius at all points. So if we have delta omega, and that is just delta theta over t, that means that your change in angular position or angular velocity, that would also be tangential. And then the question asks if you have angular acceleration that is delta omega over t, that is also going to be tangential. Okay? It is not radial. So as you increase your angular acceleration, you will increase your tangential acceleration, right? You are not affecting the radial acceleration. So it is tangential. Now, let's actually look at an equation for some of these, right? So first we have the angular equation for our other component. We have radial acceleration, right? We've talked about that as v squared over r or omega squared r. That was when we first saw omega. Now, we also know an equation for AT. AT has an equation that we've already used. to go back and forth between linear and angular. This is alpha times radius. This is the bridge equation. So when we have, x, v, and a, that's the a we're talking about. That is the exact same acceleration that we talk about when we say tangential acceleration. So we've got these two equations to get our linear components into angular components. Now, number 4 asks, derive an equation for acceleration in angular quantities. Let me erase this so I have more room to write. So our equation for acceleration, we already have up top, right? You've got acceleration is the square root of at squared plus ar squared. So if you want to get this purely in angular terms, because this acceleration of a circular motion, rotational motion, angular motion, however you want to call it, that acceleration is going to be a vector that is not along either of these axes, right? As we can see right there, like we talked about before, that is a combination of both. So let's go figure out that equation. We know that AT is alpha times r, but then we have to square that. We know that AR is v squared over r, but we don't want v, right? It asks for angular quantities. So we want omega squared times r, but that is also squared. So let's simplify that. Okay, we've got the square root of alpha squared r squared plus omega to the 4th r squared. Okay. Now, you can pull that r out of that radical to get our final answer, but I'll show that step real quick in case you guys aren't familiar. So if you factor out that r squared, you still have alpha squared plus omega to the 4th. Excuse me. So now that that r is being multiplied by that quantity, you can actually take the square root of it separately than with the others. So this would really be r times the square root, if it's as simple as it can get, r times the square root of alpha squared plus omega to the 4th. And this is our overall acceleration. Only in angular quantities, right? You need the radius and the alpha and omega, and if you have both of those, you can get the overall acceleration. And so this is just an angular version of what we already had, right? Those are linear quantities. Tangential acceleration is actually, like I said, this is the same acceleration that we use for a, v, and x. And it can be converted using the bridge equation. Now, radial acceleration or centripetal acceleration, it doesn't really fall in the XVA math that we've been doing. It's kind of a whole beast on its own, but it is still just a linear acceleration, right? It only affects in one dimension. Okay, now let's go to some examples. We're going to talk about a record player first. I know it's ancient technology for some of you, but a record player. So a turntable rotates at a constant angular speed of 33 RPMs. Some vinyls need to be spun at 45 RPMs or some are 78 RPMs, but most nowadays are 33s. Now, when the power is switched off on this turntable, it slows it at a constant rate of negative 0.173 seconds to the negative second power. How many rotations does the turntable make before coming to rest? So let's get our givens, right? We have before it starts accelerating, we have an omega naught of 33 RPMs. Okay. RPMs, that's not revolutions per millisecond. Okay, that is 33 revolutions per minute. Okay. Then we have a constant angular acceleration. Remember, angular acceleration has to be constant if we're going to use the angular kinematic equations. That is 0.173 seconds to the negative second power. We want to know the amount of rotations before until the turntable comes to rest. So we know that omega final would be 0 because it's coming to rest. So what we can do for this, we can use what we called the third equation, which is going to be omega final squared equals omega naught squared plus 2 alpha delta theta. However, we can't mix units here, right? We've got revolutions per minute, and then we have seconds inverse to the negative second power on acceleration, which means we're going to have to convert one of these. Now, it does ask rotations. So we need to keep the revolutions as a unit. So we need to convert that acceleration. So let's say that is 0.173 divided by seconds squared. So we know there are 2 pi radians for a revolution. We just won't write radians. Then you also have 60 seconds per 1 minute. But remember, these seconds are squared, which means we're going to have minutes squared. Also means you need to square your 60. So don't forget that. So our seconds go away. We will end up with revolutions per square minute. If you put that in your calculator, you should get, was it negative 99.2? Negative 99.2 revolutions per square minute. Now that we have that, we can solve for delta theta. So you would have, that's 0. So you have negative 33 revolutions per minute. That should be squared. Then you have divided by 2 alpha, which is negative 99.2 revolutions per square minute. And that will equal your delta theta. Okay, all we did is subtract omega naught over omega final was 0, so square it's still 0. You also keep that minus around. Don't square that minus away because it's a minus, not a negative. So that minus has to stay. Divide it by 2 alpha, and then you get your delta theta. Put that in your calculator, and you should get 5.5 revolutions, about, with some rounding. Now, I bring in a record player to school when we do these lessons. My turntable, when you turn the power off, it stops in about a quarter rotation, maybe a third rotation. So this takes an eternity to slow down. That is a really long time for that turntable to slow to rest. Now, number 2 asks, as the needle moves from the outer edge to the inner edge, will the linear speed increase, decrease, or stay the same, and why? So when you're playing a record, right, you start the needle on the outside, and then as it plays, it actually spirals in, right, with all of these grooves that are in the record, right? And then it continues spiraling a little bit closer, and that spirals all the way down to an inner circle. Once it hits the inner circle, there's no more grooves there, and it'll, if you've got a record player that'll stop automatically, it'll stop for you. But as it spirals down, right, that needle gets closer and closer and closer to the center, right? However, it has to spin at a constant 33 RPMs. So if it's spinning at a constant 33 RPMs, that means that that needle should be moving at the same angular velocity all the way down. However, the question asks, will the linear speed vary? So if velocity is omega times the radius, as the radius drops, you can either increase the angular speed to keep linear speed the same, or if you want angular speed to be constant, then velocity must also decrease. So that linear speed is going to get lower and lower and lower as you get further and further towards the center. You can also think about this dot. Let's say this dot right here has to keep up with this dot. Well, the inner dot doesn't have as far to go, right? It doesn't have to go as fast to make its rotation on time. But that outer dot, that needs to move a lot faster to make its rotation in time, because they have to be read at a constant 33 RPMs to make sure that the track sounds right. Now, number 3 asks, how is data off a record? That's a typo. How is data read off a record? So data is read off a record with the grooves in the vinyl. As the needle vibrates, back and forth, up and down. As it moves through those grooves, it causes vibrations, and those vibrations are read as an audio wave, and they are given to us by the record player, right? We interpret that vibration as audio, and that's how the LP works, right? LPs use a physical groove that is read through motion, and then that motion generates an audio wave. Now, is this data digital or analog? So this is analog. Analog usually has some kind of physical motion or some physical interaction to read the data. That's analog. Now, digital is very different. Digital is all in binary. Okay? Every technology that you use runs on binary. That's a series of zeros and ones that give every letter, every number in every code. It's all a series of zeros and ones. So this isn't digital, right? This is analog. It's not in binary, right? You don't have zeros and ones tapping back and forth on your LP. It's all analog. Now, digital is in CDs and DVDs, right? CDs and DVDs are a digital, which is jumping right to number one. Is this data recorded in analog or digital format? This is actually in digital format. So there are actually small pits in your CDs and DVDs, and those pits are at a specific depth, right? You've got a depth for 0, and then you've got a depth for 1. And then as it moves back and forth between these zeros and ones, the laser that's reading the disc will interpret those zeros and ones as binary. It can read the code, and it'll read your MP3 for your CD or MP4 usually for DVD. So this is actually digital format. Even though there are grooves in your CD or in your DVD, yeah, it's a physical, it's not an interaction, it's kind of physical motion, but there is a physical aspect to it, right? But the laser reads that as digital information and converts it into a digital format. All right, now, on to what the question is asking us, right? A CD is different from an LP because it has to rotate at a constant linear speed of 1.3 meters per second. And this allows the laser to read the pits in the CD at a constant rate. Now, we want to know the angular speed in RPMs when information is being read from the first track on the CD compared to the last track on the CD. And we want to know how those compare to the speed of a record player. So we have the radius of the first track. You can see off to the right, we actually have a picture of a CD, right? The first track starts at 23 millimeters from the center, and the last track ends, or it actually looks like it might be starting. That isn't all the way to the edge. So we're going to say that's 58 millimeters to the last track of the disc, right? Now we want to know how fast that is in RPMs. We want the angular speed in RPMs, right? But we do know that this must go 1.3 meters per second. If it changes from that, it's not read properly. So we have V, we have R. If we want to find omega, we can just use our bridge equation, right? V equals omega times R, so omega must equal V divided by R. So omega 1 would be 1.3 meters per second, okay? And that is divided by our radius 1, which is 23 millimeters, which we must put in meters to cancel out that meters up top. So you've got 0.023 meters. Put that in your calculator. You should get about 57 inverse seconds. Then for omega 2, you take 1.3 meters per second, divide that by 0.058 meters. And when you do that, you get 22 seconds inverse, okay? However, we want that in revolutions per minute, right? So remember when we talked about the math is made for radians, right? It's giving it to us in radians per second. So we need to convert that. So omega 1 the faster one, right? You've got 57 seconds inverse. So we want that in revolutions per minute. So we've got 1 revolution is 2 pi radians. Then you have 60 seconds to a minute. Seconds cancel. You end with revolutions per minute in RPMs. When you put that in your calculator, you should get about 544 RPMs. That's for the first track on the CD. For the last track on the CD, you have 22 seconds inverse. You have 1 revolution for every 2 pi radians. And then you have 60 seconds per minute. So seconds are gone. Revolutions per minute. You then get approximately 210 RPMs. Now, if we compare that to the measly 33 RPMs that most LPs are read at, this is going really fast. And when you guys watch a CD, if you've ever had like a clear case CD player, which a lot of CDs nowadays do, you can see that CD is going really fast, right? And it actually has to change how fast it's going depending on which track it's reading. Now, I don't know if you'd be able to notice a difference between 210 and 544 RPMs. I've never looked at that. That might be just too fast that my eyes can't comprehend it. But that'd be interesting to see. If you've got a clear CD player where you can see through the top, see if you can notice the change in speed between the first and last track. So play the first track, then skip to the last track, and see if you can notice it. Now, last question on this slide says, what is the total length of the path that moves past the lens for a full-length CD that plays 74 minutes and 33 seconds? So 74 minutes, 33 seconds is supposedly I believe that's the limit that you can have on an album, on a CD. So we want to know, what is the total path of grooves? Like how long, if we were to take that entire CD groove, right? And instead of spiraling it from the inwards out, let's just stretch it out. How long would that actually be? So let's see. So we do get a hint on this problem, right? It says this is easier than it looks, and that says KISS. KISS stands for keep it simple, stupid. So if we have the velocity at 1.3 meters per second, and we have the time at, 74 minutes and 33 seconds. So let's see, that would be 74 times 60 plus 33. Okay, what is that? That is 4,473 seconds. So you've got 74 seconds. So we have velocity, we have time. What we want is we want the total path, right? We want the arc length, S. So we do have the equation S equals VT. Okay, if it's a constant velocity, you just see how far you would travel if you go at this velocity at this time, right? That's just basic position math. So we take S equals 1.3 times 4,473 seconds, and you would get approximately 5,800 meters, which is 5.8 kilometers. So if you guys have ran a 5K, a CD is longer than that. The groove in there is longer than a 5K, which is nuts. It's almost 6K. But that's also how tiny those little grooves are. I think they're measured on the micron scale. So it's a really small path that they're working with. And when you wind it that many times around this, that's only 35 millimeters in width, right? From 23 to 58 millimeters, that's a long ways. All right, we have one more problem that we're going to do. From number 3, we know that the maximum playing time of a CD is 74 minutes and 33 seconds. How many revolutions does the disc make during this time? And then it asks us to graph omega versus R. So we have the omega versus R information, right? We have 1 point of omega 1 was, what was that? That was 57, right? So let's do r omega. Okay, we want the radius to be in the x component, right? So we've got a radius of 23 millimeters. Then you have an angular speed of 57 radians per second. Then our second point would have 58 millimeters, right? Yeah, whoops, pen freaked out. So you got 58 millimeters, and then a speed of 22 radians per second, right? So let's make this graph. Okay, we start, let's see, we need to go up to 60. So let's see, there's 60. If you're 30, you're 15, then we'll split that into 5 and 10. 20, 25, 30, 35, 40, 45, 50, 55, 60. Okay, so we'll do that. Then we need the same up here. So, that needs to be longer. Okay, so we'll call, you should be about 60. So you would be 30, you'd be 15 and 45, then you've got 5 and 10. I know that's not perfect, but we'll go with it. So we start at 23, let's see, 15, 20, 23, about right there, up to 57. So that's really high up here. There's our first point, right? Then we go to 58, which is way on the right, down to 22. So if this is 30, 15, 22, about right there, right? So those are our 2 data points, right? However, we know that omega and r have an inverse relationship, right? Omega is v divided by r. So this is not a linear graph. I don't know that that's going to be the right curve. Honestly, that looks a little too horizontal at the end, but there we go. It's not going to be linear, right? It's got this inverse relationship similar to a 1 over x relationship, right? It's going to have that exponential curve to it. Now, if we want to know how many revolutions this disk makes, right? Excuse me. So we want delta theta. Now, delta theta, you can just like we did before, right? Was S equals VT for distance traveled. So we need omega t to find theta, but we don't have a constant omega, right? So we would need some average omega to do this problem. But we also don't have a linear graph. So how do we find the average of a nonlinear function? So this is interesting, okay? If you take the area of the graph, okay, area of that graph, then divide that by the range of the x-axis, okay, then you could get the average value within that nonlinear graph. So if we want to do that, okay, the area of the graph is going to be the integral of omega with respect to the radius, right? Because it's a r versus omega graph. And then the range of x, that's just 57 minus 20, no, 58 minus 23. Oh, wow, if you notice that, they're almost completely flip-flopped. That's interesting. You've got 23 and 22, 57, 58. That's kind of cool. So we have, what are we doing again? Range of x, right? So the range of x is going to be just delta r, which is 58 minus 23. That's 35 millimeters, which is 0.035 meters, right? But we want to integrate omega. So let's work on this integral. Okay, we are integrating, let's see, we're integrating from 0.023 to 0.058. All right, 23 to 58, yeah. So, and we want this in meters, so that's why we've got these complicated decimals. But we also know that omega equals v divided by r. So we can actually integrate v divided by r because an r is actually present, right? If you integrate omega, there's no r present. So we would get the integral, let's just say from R1 to R2, of V divided by R dr. And the integral of 1 over R is natural log, right? So that's basically the integral of V from R1 to R2 of 1 over R dr, right? So then you have V times the natural log of R from R1 to R2, right? So what we'll do here is we will plug that in. You've got V times the natural log of R2, which was 0.058, minus the natural log of 0.023. Okay? And that's what we're going to stop with, okay? Because that's the area of the graph. Let's stop there, and we will move that up here. The area of the graph is V times the natural log of 0.058 minus the natural log of 0.023. Okay? Divided by the range of x, which is your delta r. Okay? And that delta r is 0.035. So if you put that in your calculator, your omega average is going to come out to approximately 34.36 radians per second. Okay? If you plug in V for your 1.3 and 0.035 for your delta R. Okay? However, we want revolutions the disk makes, right? Remember, this is our goal. But we want that in revolutions, so we need to convert this. We've got 34.36 divided by seconds. And we need, what is our time? Our time is in seconds, right? We figured that out. That is 4,473 seconds. So we can keep it in seconds. We just need a revolution in there. So there's 2 pi, 1 revolution. That will give us, that gives us 5.47 revolutions per second. And then for delta theta, we've got to multiply 5.47 revolutions per second times 4,400, what was that? 4473 seconds. So that gives us 24. 24,460 revolutions, basically 24,500 revolutions. That was the bell at my school, so luckily that was the end of our video, and next time we will pick up with some torque.